to the organizers for putting together the conference and for giving me the opportunity to speak. So my talk today is about a class of like 2+1 dimensional quantum lattice models, which in some sense generalize the anyon chain. And in particular, I want to talk about dualities between these models. And my talk is based on my recent arXiv preprint as well as earlier work with Paul Fenley. Okay, so as a condensed matter physicist, I'm interested in understanding quantum phases of matter arising in models governed by some local Hamiltonians. And in 1+1d, the anyon chains are a particularly nice class of toy models, which naturally come with categorical symmetries as well as dualities between different models. And in this context, what I mean by duality is that two Hamiltonians are dual if their local terms generate the same algebra. So in particular, these Hamiltonians can be defined on different Hilbert spaces, can have different symmetries, but this notion of duality imposes constraints on their energy spectra. So these models should have the same energy levels, but with different energy, but with different degeneracies. And this notion of duality includes the gauging of discrete symmetries. So we can use these symmetries and dualities as tools to constrain the phase diagrams of these anyon chains, which can look quite rich, have many interesting gapped phases as well as gapless transitions. And as we've heard this morning, there are also many connections to conformal field theory as well as integrability. Now in 2+1d, yeah, okay.
I see, so I will take my question back. So the diagram is very interesting, but I didn't read what it said on top, which is 1+1d. So this is 1d, and then later
that's all 1+1d. It was just for some motivation, 1+1, like, I don't know. The upshot is anyon chains are nice in 1+1d.
Thank you.
Okay, so now comes the more difficult part, so let's go up one dimension into 2+1d. And now things are really complicated, so commuting projector models like the Lagrangian string nets can realize all types of non-chiral topological orders, but we can't get chiral topological orders, which have gapless protected edge modes. And there are some ways to go around this. For example, we can place string nets on the surfaces of like 3+1d Walker-Wang bulks, and this was done in some like recent literature. Another possible route is to move beyond commuting projectors and consider models whose local terms don't commute. And one example here is KITP's honeycomb model, which has chiral Ising topological order when time reversal symmetry gets broken, and which can be solved exactly with free fermions. Now, KITP's honeycomb model is very special. And in my talk today, I want to explore like a broader class of 2+1 dimensional models, which also are not of the commuting projector type. Now, the big disclaimer is that these models are not exactly solvable as far as I know. So basically, in order to understand their phase diagrams, I do rely on like numerics or some like approximate arguments. However, because these, I will build these models from Inamura and Omori's fusion surface model framework, and this still guarantees me that they have some nice exact categorical one-form symmetries, which can at least help me to get some handle on their phase diagram. And in my talk, I also want to talk about dualities, which will basically be kind of like the gauging of these one-form symmetries. And I just want to point out that there's much literature kind of like going the opposite way and starting with like zero-form symmetric models and then gauging the zero-form symmetries. Okay, so the plan for today will be to do like a super brief recap of 1D and then talk about the fusion surface model construction in 2+1D. Give some examples for phase diagrams, and then mostly talk about these dualities, how we can construct these, and some examples. It turns out that the right mathematical framework for getting these dualities will be enriched fusion categories. So if you know what this means, then yeah. Okay, so basically I will need two mathematical concepts for my talk: fusion categories that you're probably all familiar with by now, and module categories. I will denote the objects in the fusion category by Greek letters, and I will use the graphical calculus where the lines are labeled by objects in the fusion category. And these trivalent vertices correspond to allowed fusion channels. I will only consider multiplicity-free fusion categories here, so this coefficient is always 0 or 1. A module category over a fusion category appears in contexts like gap boundary conditions of topological orders or the SymTFT. And the module category can have a different set of objects, which I denote with Arabic letters, and it also comes with an action of the fusion category on the module category. Pictorially, this actually means that there's some kind of vertex where we have two lines of the module category meeting one line of the fusion category. Now, these fusion spaces here can be higher dimensional, and so I label them by a basis vector. The module category also has its own set of module F symbols, and one choice for a module category that we can always make is we can always just take the fusion category as a module category over itself. That's called a regular module category. Okay. So taking the fusion category and the module category as input, we can construct an anyon chain. So this notion of anyon chain is a bit more generalized. Now basically the Hilbert space is determined by the module category. So these edges here are labeled by objects in the module category, and the vertical legs are all labeled by one fixed object row in the fusion category. Then the local terms in the Hamiltonian correspond to basically fusing a line labeled by an object in the fusion category to these legs, and then evaluating this using the module F symbols. And this construction gives us two key payoffs. So the first one is that we basically get the symmetries for free. So the symmetries are labeled by objects in the Morita dual fusion category, which, if we take the regular module category, is just like the fusion category itself. And pictorially, they correspond to having lines which are fused onto this fusion tree from above. The second is that we get duality mappings between anyon chains constructed from different module categories over the same fusion category. And this is because basically the bond algebra of the terms in the Hamiltonian only depends on the fusion category, not on the module category. And these duality maps can be written out explicitly as matrix product operators. Okay, so let's do an example that I will later redo in 2+1d. So we take the rep S3 category as input. I will denote the non-abelian object by 1 here because it has this like spin 1-like fusion rule. Then with the regular module category, we get some constrained Hilbert space because the objects 0 and 2 always have to be next to edges which are labeled by 1. And there's a physical interpretation of this in terms of Rydberg atoms on a ladder. On the other hand, if we take the trivial module category, then we find a tensor product Hilbert space of qubits which sit on these trivalent vertices. And for this model, we can pick the Hamiltonian to be the XXC chain Hamiltonian, which is very well studied and known to be critical when delta is between -1 and 1. And so because of this duality mapping, we can immediately infer that like the corresponding dual Hamiltonian must also be critical for delta being in this range. Even though this is like far from obvious if you just look at the Hamiltonian and didn't know about the duality. Okay. So now let's move up one dimension. The original proposal by Inamura and Omori takes fusion 2 categories as input and then produces 2+1d lattice models which have both 0-form and 1-form symmetries. And their graphical calculus involves surfaces. Now, kind of like the practical problem with this is that we just don't know the 10J symbols of the fusion 2 categories. So we can't really write down the Hamiltonians explicitly. So what I do in my work is I make a big simplification. I only use a braided fusion 1 category as an input, which means that the surfaces are trivial. But I know the data of braided fusion 1 categories, and so I can actually write down Hamiltonians. So this works like here. So you should compare this to basically like the regular anyon chain construction where the module category is just a fusion category. So I have two pieces of input here, the braided fusion category, and again the specified object row. And you will see in a moment why we need the braiding. So then the 2+1d states correspond to diagrams like this, where again all these like vertical blue legs are labeled by row, so these are fixed, and the degrees of freedom live on these black edges. Then the Hamiltonian that I will choose for this talk is basically this one. So it has 3 different terms. This JZ term is basically just the local anyon chain Hamiltonian, but the JX and the JY terms couple more degrees of freedom. And they also involve like an undercrossing of this black line with the blue line. And this tells me that I need some sort of braiding. I can work out the Hamiltonian explicitly just using like the F symbols and the R symbols of the braided fusion category. And because the R symbols are complex phases, it can very well be that the Hamiltonian is not real and breaks time reversal symmetry explicitly. By design, this model has categorical one-form symmetries labeled by objects in the input braided fusion category. And these show up as mutually commuting plaquette operators, as well as kind of string operators acting on incontractable loops. Okay, so kind of like the key example for this is rewriting Kitaev's honeycomb model as a fusion surface model constructed from the Ising category. So to do this, these vertical legs are labeled by the non-abelian object sigma, and then the Hilbert space is written in such a way that we have like the abelian objects on this subset of edges, and then the other edges are also labeled by sigma. So effectively, we get a tensor product Hilbert space of qubits located on the vertices of some effective honeycomb lattice. And then the Hamiltonian is constructed by fusing the abelian line to these vertical legs, and one can show that this is unitarily equivalent to Kitaev's honeycomb model. And as I mentioned in the introduction, Kitaev's honeycomb model has an interesting phase diagram where these phases here are toric co-topological order, and the phase in the middle is gapless. But when we add a small perturbation that breaks time reversal symmetry, this becomes chiral Ising topological order. Yeah.
All the one-form symmetries preserved? In this Hilbert space, all the one-form symmetries preserved, or do you only break it to Z2?
I only have Z2 in this case.
So you don't have the sigma as a one-form
The
symmetry?
sigma gives kind of like a duality, but it's not a symmetry. Yeah.
Thanks.
So if you use the braiding, how can be Hermitian automatically, the Hamiltonian?
I think this is guaranteed by Inamura and Omori's construction, but it's not obvious.
Yeah,
so
okay.
basically, you do have to do some kind of computation to show this.
So it is Hermitian.
It is Hermitian, yeah.
Okay.
Okay, then basically kind of like the main point from my paper with Paul was to say that different braided fusion categories inputs give me kind of like generalization of Kitaev's honeycomb model in the sense that the models will still have exact one-form symmetries, which give rise to these mutually commuting plaquette operators. And we also expect them to have a qualitatively similar phase diagram. So we can show that when one coupling constant is dominant, the model basically reduces to some effective string net and has non-chiral topological order. At the red points, the model effectively becomes kind of like a stack of gapless decoupled anion chains. And so we conjecture that there's like one phase in the middle, which should be qualitatively described by weakly coupled anion chains. And if time reversal symmetry is broken, this is where we could expect to have some kind of chiral topological order. And indeed, we looked at kind of like two examples, one constructed from the Tambara-Yamagami Z3 category, which recovers a model that has already been studied in the literature like 10 years ago. And there's very good numerical evidence that this has chiral topological order, even though it's not clear which one. And then we also looked at like a Fibonacci model, which looks more exotic because of a constrained Hilbert space. And yeah, it could be that this Fibonacci model also has chiral topological order, but we can't say for sure. Okay. Yeah.
Oh, what's the general rule of what part of B will be a symmetry? Like in the Ising case, it wasn't Ising, it was Z2. What's the general rule?
Yeah, that's kind of like Tambara-Yamagami is special because you fix some of the edges in your Hilbert space to be labeled by sigma.
But can you state it in terms of this abstractly? Like what about the braided fusion category?
I'm saying basically the only exception is Tambara-Yamagami. Is Ising. Otherwise, the symmetry should be labeled in B.
I see. So for every Tambara-Yamagami, I'll just not have the non-invertible part of the symmetry and only have the invertible.
Yeah.
But for every other braided fusion category, I'll have the full braided fusion category symmetry.
Yeah, that's what I would say. Yeah.
I see. Okay, thanks.
Sorry, a follow-up. Is it related to a grading on the braided fusion category? So if you have a Z2 grading, you are only focusing on sector with zero grading?
No, it's really basically because I'm fixing some edges in the Hilbert space to be labeled by sigma. So basically, similar as in the 1+1d anion chain Tambara-Yamagami case, your Hilbert space decomposes into like decoupled sectors, right? And yes. Basically the sigma line is kind of like mapping between these decoupled sectors.
I agree. But is it related to a Z2 grading on the fusion rule? So 1 and Z2 have trivial grading, but the sigma has a grading 1. So you only pick
in this special, I guess you can see it this way. Yeah.
Okay, thanks.
Okay. So now I want to talk about how we can extend this fusion surface model construction. And the strategy will be very similar as in 1D. So again, we want to kind of like refine this input by the choice of a module category. So now we want to label these horizontal edges which make up my Hilbert space, again by objects in a module category over the braided fusion category. But these 2+1 dimensional diagrams, they involve like a vertex, like a trivalent vertex like this, where 3 objects of my module category meet. And so this tells me that it's not enough to just consider a module category, instead I need a module tensor category. So this also has a tensor product between its own objects. And this is like a well-established concept in the mathematical literature, and it's often also called like a B-enriched fusion category. Okay, but basically, so you can kind of like view these module tensor categories over the braided fusion category as like a categorification of like the module categories over fusion categories that we needed in 1+1D. And then basically everything goes through as before, so we can define the Hamiltonian in the same way. And now we get dualities between Hamiltonians built from different module tensor categories over the same braided fusion category, because again, the bond algebra of these Hamiltonians only depends on B, not on M. And just as a side comment, in order to work out these Hamiltonians explicitly, we now need kind of like additional F symbols, additional half braiding phases, but in principle one should be able to get these from consistency equations like the hexagon and pentagon equation. Okay, so now let's repeat the example that I did in 1D. So again, we take rep S3 as an input, and now we also need to choose a braiding, and I will choose the symmetric braiding, so all braiding phases are real. Well, then if we take this regular module tensor category, we just get again some model with a constrained Hilbert space. And this model is guaranteed to have a rep S3 one-form symmetry. On the other hand, we can also take the trivial module category again, and now we will get again the XXC model basically, but now defined on an effective honeycomb lattice because the qubits live on these gray vertices. And this model, of course, doesn't have any one-form symmetries, but it has an S3 zero-form symmetry. And so you can see the duality basically as kind of like gauging like the rep S3 one-form symmetry.
Question.
Yeah.
I have a question about the 2+1D model and also for the 1+1D.
Okay.
How does the S3 act?
I mean, it's like a subgroup of like the U1 magnetization and the Z2 spin flip. In the XXC model.
Yeah. Like in 1+1D XXZ, why is there S3 symmetry?
It's just kind of like the finite subgroup of like the U1 times the Z2 spin flip.
Oh, I see.
Yeah. So yeah, it's actually larger, but like,
I see.
yeah.
Part of the...
It's part of like, yeah. And then kind of like the point is that, again, this XXC honeycomb model, it's known in the literature. There has been many numerical studies on this. And in particular, it's known that in this phase here in the middle, we have like antiferromagnetic order when delta is larger than 0. And then in addition to that, delta is smaller than 1, we also get gapless-Goldstein modes because the U1 symmetry is spontaneously broken. And so again, we can infer something about the phase diagram of this very exotic looking model. So we can infer that this phase here should also be gapless in this particular regime.
Question.
Yeah.
So if I naively gauge S3 on that side, I can end up in a non-constrained Hilbert space, right? So why does that happen in your case?
I'm sure there are like different ways how you can do the gauging. I'm just saying that kind of like from kind of like the symmetry structure, it looks like my kind of way of implementing these dualities is basically kind of like gauging the rep S3 one-form symmetry. So basically, I'm going from this model kind of like to this model, I would say.
I guess my question is going the reverse, because naively I would think gauging S3, you can end up in a tensor product Hilbert space, right?
Yeah, I'm sure you can. This is just like one way where you don't. Yeah.
Maybe this is a different
Okay. Then just to flash like another example, so we saw that if you input the icing category, we get Kitav's honeycomb model. And now if you input 2 copies of icing, it shouldn't be too surprising that we get like a bilayer model of like 2 copies of Kitav's honeycomb model with some interlayer coupling, which is just like the product of the 2 local terms. This model will have 2 Z2 1-form symmetries, 1 for each layer. And it has been studied before in a recent paper because its phase diagram is kind of interesting. So this is at the isotropic point, and we tune the interlayer coupling. And when it's small, then basically we have kind of like 2 decoupled chiral icing spin liquids, which together make up non-chiral icing times icing bar topological order. And then when delta is large, one can map the model to a quantum diamond model on the Kagome lattice and find toric code topological order. And so this transition is basically some anion condensation transition, which should be in the 3D icing universality class. And then again, we can play the same game and like pick a module tensor category over icing times icing. So we can just pick basically 1 copy of icing. Then we get some different model on a different Hilbert space. So we have, it's again a tensor product Hilbert space of qubits. We have qubits on these red vertices and also qubits on the red links. And now we have a Z2 1-form symmetry as well as a Z2 0-form symmetry. So it looks like my duality has kind of like gauged the diagonal Z2 times Z2 symmetry here. And now it looks like, so the phase diagram, so no one has studied the model before, but it looks like we have toric code topological order basically throughout. But when delta is large, one can do perturbation theory and like show that basically these vertex qubits here freeze into ferromagnetic ground states, breaking the Z2 0-form symmetry. And so the transition is now just like a Z2 symmetry breaking transition, which again should be described by the 3D icing conformal field theory. Okay, so that was just another example, and basically the interesting thing is that here we get like kind of like a mixture of like 0-form and 1-form symmetries. Okay, so you might have noted I haven't told you what like the symmetries of the dual models are, and that's for a reason, because that's kind of like the difficult part. So in 1D, we know that the symmetries are the Morita dual of the fusion category with respect to the module category. And the same should hold in 2+1D, just 1 categorical level up. So the symmetry should be in the fusion 2 category, that is the Morita dual of mod B with respect to mod M, where mod means condensation completion. And there's been some discussion of this particular fusion 2 category structure in the mathematical literature. And what I understood, there are kind of like 2 key takeaways. So the first is that the 1-form symmetries should be labeled by objects in a Drinfeld center of M that braid trivially with B. And this braiding trivially condition means that we can like freely deform the 1-form symmetry past these blue lines. The difficult part is finding the 0-form symmetries. Their existence depends on a certain functor. So this braided functor is guaranteed by this modular tensor category structure. It goes from B into the Drinfeld center of M. And if this functor is fully faithful, then we only have 1-form symmetries. And this is assumed in like recent papers on string nets on Walker-Wang bulks. If, however, this functor is not fully faithful, then we get independent 0-form symmetries, and that's what we saw in the examples. But what exactly these 0-form symmetries are and how they act on the lattice, I don't know, like in all generality. So that's something which is still kind of like, yeah, an open question. And another side comment, so it is known that all fusion 2 categories are Morita dual to some mod B, and this implies that basically we should be able to realize all types of fusion 2 categorical symmetries in some of these extended fusion surface models. Okay, so basically here are my conclusions. So by refining the input of the fusion surface model construction from a braided fusion category to a pair of categories, a module tensor category and a braided fusion category, I got kind of like a larger class of models, including ones which are well known in condensed matter physics, like the XXC honeycomb model. We also got dualities between these different models that we can use to get constraints on the phase diagrams. And finally, we get models which have both 0-form and 1-form symmetries, that these are candidates that might have some kind of like symmetry-enriched topological order. And as for future directions, I think it would be interesting to think more about these symmetry-enriched topological phases in this context. It would also be interesting to think about like self-dual fusion surface models if they realize some kind of critical points. And finally, this 2+1d dualities could be useful because in tensor network simulations, it's better when the symmetries are broken. And so one could use dualities. One could use dualities to map to a model where the symmetries are broken. Okay. Yeah.
So in one of the slide, you shows that if you take the double icing, I think we'll go to toric code. Then the transition is a 3D icing. So there are 8 versions, or at least 4 versions of this transition, which is toric code. If you gauge toric code, there are many different icing. Do you think they all give you the same 3D icing transition?
To be honest, I don't know.
Okay.
I haven't looked into this transition very carefully. It's just basically kind of based on this anion condensation picture that it should be some 3D icing, but yeah, it's a very good question. I don't know.
Okay, there's an even more interesting case to study, which is you can take double S3 and condense A plus C to get toric code. That's not a group subcategory. It's a condensable algebra. I wonder you get something exotic or you get 3D icing also.
Okay, that's a very interesting question.
Yeah, there's a very interesting transition from double S3 to toric code.
Okay, thanks.
Thanks for the nice talk. So I have a question. If you take the Levin-Wen model, is it a special case of the stringnet model? Is it a special case of here for a braided fusion category when it's just some?
Yeah, you can view it as a special case when you basically just label the vertical legs by the identity object.
Okay, good. So now in that case, you could take a Lagrangian algebra and gauge the one-form symmetry. Then presumably there is some dual fusion to category.
Yeah, I guess.
And you have some model also for that. My question is that does that model coincide with the model that was discussed by David Pennies and Corey Jones and others that he gave a talk about it 2 weeks ago? That said the Levin-Wen is a gauge theory. So they were doing the other direction. They were starting with some theory gauging tube algebra to get Levin-Wen. Is that gauging or duality part of your story?
I think their gauging was a bit different because they had an SPT phase, right? And then and it was always an SPT, and then they got to their stringnet. So I think it's a bit different.
But we also expect that if you start from stringnet or Levin-Wen model and gauge a Lagrangian algebra, we should also go to a trivial phase. And maybe that's their SPT in some sense, which has some fusion to category. Yeah. They didn't just discuss a fusion to category, but.
Yeah, I would have to think about it more, but interesting question.
Thanks.
Oh, I have a question. So, in which case do you know? So given a B and M, do you know when the Hilbert space is not constrained Hilbert space? Is it really a tensor factorized Hilbert space?
I'm not sure if there's a general rule. I guess in most cases you would always get a constrained Hilbert space. It's kind of special when you don't get one.
That's right.
And these very simple cases where you just take the trivial modular category, and then basically have degrees of freedom only living at these trivalent vertices, and so then it's kind of like a tensor product. But I think in most cases you will get a constrained Hilbert space. Yeah.
Thanks.
What do you mean?
Like if it's nilpotent and then you just put your external leg to be the largest one, and then the Hilbert would be tensor product where you restrict to the zeros, the smaller sector.
Okay, sorry, I'm not sure I follow. What is nilpotent?
Oh, it means that when you fuse together, stuff gets smaller always.
And wait, your claim is that if I'm taking some nilpotent fusion categories input, I will get some.
Probably, that's my guess, that it would be tensor product.
I see, okay. It's interesting. No, I don't know, but it's an interesting question.
So I think throughout the talk you assumed the braided fusion category was multiplicity free, is that right?
Yes.
Is there anything, do you know anything new would come up if you went beyond multiplicity-free braided fusion categories?
I don't think it would be much different. I just like made this assumption so that I don't have to like draw dots in my diagrams all the time.
I see. I mean, is the definition of the 2D model different, or is it the same?
It's basically like the same. I mean, then you could get kind of like, then you could get kind of like additional degrees of freedom, like living also at these vertices, right? So the Hilbert space would be kind of potentially larger. The terms in Hamiltonian would potentially couple more degrees of freedom, but you could absolutely do this.
Okay, thanks.
Hi, thank you for the nice talk. I have a sort of a understanding question again. So when you say these B phases are sometimes chiral and sometimes not chiral, what's the mechanism you detect this with? What makes it chiral?
Like the thing is, I mean, I never know basically a priori. So one strong hint is that when the Hamiltonian breaks time reversal symmetry, then kind of like that's not a proof, and it doesn't have to be that we get chiral topological order, but it's at least sort of like more likely. And that's why, for example, like here, I wouldn't expect chiral topological order because we have like symmetric braiding, so the Hamiltonian is real. But like in the set 3 honeycomb case, the Hamiltonian breaks time reversal symmetry, so it's kind of like more natural. And then basically in order to really show that it has chiral topological order, one has to do like numerics, for example, and show that it's gapless if you put it on a strip.
Thank you.
So what happens if, with the topological sectors, if you do these kind of if you choose the different modules?
Yeah, that's a good question. So I haven't worked it out explicitly, but there should be, similar as in 1+1d, there should be like kind of like mappings between different topological sectors. But now it's kind of like more complicated because I get, I need to consider like the symmetry twisted boundary conditions. But now I guess I could get symmetry twists both from like one form and from zero form symmetries. And I'm not 100% sure how I would like organize this basically. Yeah.
Any more questions?
I had a small question. I realize it was not the main point, but in the beginning you mentioned your 1D work, where you had the integrable Rydberg ladder. I was just confused. Sorry, not confused. I was just wondering, do you just use the Hamiltonian? Is it the usual PXP type Hamiltonian, or do you need extra terms to make it integrable? How come?
Yeah, it's kind of like a fine-tuned integrable version. So yeah, it's not like the generic like PXP type Hamiltonian that you would write down.
Can you give a sense of what the interactions look like, or is it hard to just maybe I should?
So the Hamiltonian is a bit long to write down, but I mean it has some like particular kind of like terms which like flip, I don't know, which change like which allow me to like change particles from top to bottom. And they also have some like next nearest neighbor interactions, so not only nearest neighbor runs some chemical potential.
Yes.
But yeah, there was actually like recent like numerical paper by Natalia Chepiga showing that basically even if you take like the generic like PXP Hamiltonian on such a Rydberg ladder, you get kind of like similar phase transitions in the phase diagram actually. So it seems that even though our Hamiltonian is pretty fine-tuned, it still retains like the phase diagram seems to be similar.
Okay, thank you.
Good. Let's thanks Luisa again.